Right now, as you listen to me, something inside of you is bouncing up and down up to 10,000 times every second. What is this? I'm talking about something inside your ears, something which enables you to hear. Cochlear hair cells. These tiny finger-like projections line the cochlea of your inner ear. The cochlea is the spiral-like structure on the right-hand side here. And this is a massive magnification of your cochlear hair cells. As I speak, my vocal tract vibrates, producing sound waves with frequencies of up to 10,000 waves per second. Your cochlear hair cells detect these waves and actively bounce up and down in response to every single wave. Each bounce generates a small electric signal, which is sent to the brain. When it reaches the brain, we hear sound, which is how you know that I'm talking right now. Today we will see how knowledge of cochlear function could be used to reverse hearing loss from the inside out, a biological treatment rather than the imperfect electronic treatments used today. So like anything in life, the hearing system doesn't always function perfectly. Loud sound, toxic chemicals, sickness and aging can all damage the hair cells. This is permanent damage. Rather than being healthy, upright projections, as we can see here, and on the left-hand side here, the damaged hair cells lie flat and stuck to the cochlea. Not surprisingly, they can't bounce about when they're lying in a messy heap, so nor can we hear properly. This form of damage is the most common cause of hearing loss in New Zealand and in the world. But why is this damage irreversible? Why is it permanent? Other cells in our body can grow and repair. If you get a cut on your skin, you're not left with a permanent wound for the rest of your life. So why should these be any different? The human body does contain all of the genetic information it needs to regenerate these cells. It just can't use it because these genes are turned off. Now this is where the science becomes incredibly exciting. What if there was some way we could turn these genes back on? The answer may lie, or rather fly or leap, within birds and frogs. It was always thought that hair cell damage is permanent, irreparable. This previous way of thinking, or paradigm, stopped scientists from making a major discovery in the 1930s. Back then, experiments on frogs suggested that their cochlear hair cells could actually regrow after damage. The scientists, however, did not think this was possible. It didn't conform to our previous way of thinking, so the evidence was ignored. Again, in the 70s, experiments on frogs suggested that loud sound and toxic chemicals didn't damage the frog's hearing. The scientists puzzled over this. They altered the experiment a little, hoping to get different results, but eventually dismissed the project, deciding it was a complete failure. It wasn't until 1988 that the paradigm finally shifted. Two scientific groups in the US looked at quails and showed that their auditory hair cells did grow back after damage. They showed this in detail. This finally revealed that hearing repair is possible. It's also a valuable lesson for all scientists. We shouldn't dismiss scientific findings simply because they don't follow the current thinking. This evidence was staring right in the eyes of scientists, and yet they didn't accept it. So the question now is, if birds and frogs can repair their hearing, what about us? I'm interested in using these animals as models to understand the molecular and genetic systems they use to regrow hair cells. This information could be used as a permanent biological treatment for the most common cause of hearing loss in New Zealand. Now let's take a quick look at some of the issues with current hearing treatment, including hearing aids and cochlear implants. Despite major advances in these technologies, they are far from perfect and cannot restore normal hearing. Take hearing aids, for example. They're expensive. They can whistle, buzz, sound tinny, and make your ears itchy. They need battery changes and wax cleaning, and they can amplify all sorts of sounds that we don't actually want to hear. Now, cochlear implants bypass the hair cells entirely. Despite the sophisticated circuitry they contain, they cannot come close to what the ear does naturally. So rather than inserting electronic gadgets into our ears, we could use the body's own existing genes to regenerate cochlear hair cells, fixing hearing loss from the root of the problem. Now, genes are complex things. Whether they are turned on or not depends on the environment around them, including any chemicals present in this environment, and even the activity of neighbouring genes. By studying birds and frogs, we could reveal their secret. Treatment for hearing loss may involve identifying a chemical, a natural product present in these animals that genetically stimulates hair cell regrowth. We could produce this product. We could develop it using pharmaceutical innovation to lead the world in hearing healthcare. Now, hearing loss is a lot more common than you might think. Sitting in this room today, I would expect not only myself, but around 10 of you to also have some form of hearing loss. That is, 1 in 10 New Zealanders do have a hearing loss. This issue is especially important in New Zealand because the incidence of hearing loss in our Māori populations is even higher, around 1 in 8. In the younger generation, it's up to 4 times more prevalent. The issue doesn't stop here. There are predictions that in the near future, the incidence of hearing loss will dramatically increase. The social burden of hearing loss is immense. Impaired communication can cause social isolation, embarrassment, a fear of talking. Cochlear implants and hearing aids are like a band-aid. They're visible and intrusive, a constant reminder of our imperfections. Individuals with regenerated hair cells, however, would simply no longer have a hearing loss. Hearing impaired kids would have equal learning opportunities. When we can hear properly, we are safer, more employable, and it is easier for us to understand and contribute to the world around us. Now, current hearing technology is also a financial drain on individuals and the government. And also, hearing impairment, improving New Zealand's ability to hear would actually hold a strong economic benefit for all of our society. The hearing impaired are significantly less likely to leave school with a formal qualification. As adults, they are more likely to be unemployed. Between 1996 and 2001, only 41% were employed or seeking work, and those employed were more likely to have a low income. So now the financial side. Hearing aids cost between $3,000 and $9,000 per pair, and this cost isn't going down, while cochlear implants are around $50,000 each. The New Zealand Ministry of Health provides full payment and subsidises treatment for some users. Not only are these upfront costs immense, but the maintenance, support and replacement costs are ongoing. If we can discover the secret of birds and frogs, no longer will we rely on importing hearing technology from overseas. Instead, New Zealand could lead the world in pharmaceutical innovation, offering a likely less expensive but more effective hearing loss treatment. Clearly, this has a business potential too. We could produce this product and market it overseas. A further advantage, it is likely that a biological treatment would have a smaller environmental impact than the production and disposal of hearing aids, cochlear implants, and batteries. So why should New Zealand solve this problem? There is a great capacity for molecular biology and genetics research within New Zealand. For example, Genetics Otago is the largest centre for advanced genetics research in all of Australasia. The IIB in Auckland attracts researchers from around the globe to do studies of this calibre. Also in Auckland, there is an active team looking at the molecular basis of deafness. These centres and others could be extended to look at cochlear hair cell regeneration, with a focus on animals like birds and frogs as models. They could collaborate with our 2 existing audiology departments in the Universities of Canterbury and Auckland, working together to provide a better, innovative treatment for hearing loss. So today we have seen how the cochlear hair cells are vital for us to hear. We have found that humans do not regenerate these hair cells throughout life, but other animals like birds and frogs do. This reveals the exciting possibility for hearing repair in humans. Now let's consider the words of Helen Keller, an inspirational social activist and writer born in the US in 1880. Blindness cuts us off from things, but deafness cuts us off from people. Helen Keller was both blind and deaf. She went through an enormous struggle to overcome her social isolation and learn to communicate. New Zealanders would have the choice to reconnect back to people. Institutes within New Zealand could research a unique pharmaceutical product, one that regenerates these cochlear hair cells using the body's very own existing genes. We would reduce financial strain on individuals and the government. We would increase employment and education prospects in New Zealand. We would improve the lives of all New Zealanders, especially those who are hearing impaired, their friends and family around them. It would be the beginning of a time and place where hearing loss becomes almost unheard of. New Zealanders would cure their own disability, and it is all already in our genes. Thank you.
Hi, Lara, thank you. Just as a matter of interest, why do you think the cochlear hair cell regeneration gene is turned off? Or is it that we simply never had one?
We do have one, and it's turned on during embryonic development. The reasons why it turns off is sort of under an evolutionary debate at the moment, but some of the likely reasons for this is that anything which is produced throughout our lives is energetically demanding. So back in the day where maybe we had fewer chemicals in our environment, we had less loud sound surrounding us, it wasn't essential for the human body to regenerate these hair cells. So it was just an energy expense which wasn't needed. So it was selected against. And now as we encounter more chemicals and more loud sound, more sicknesses and things, it's becoming necessary for us to regenerate them. But evolution in humans hasn't caught back up to it.
It's possible, however, that we can't afford it yet either. In other words, if we turn it back on, something else will have to be turned off.
There's always going to be an interplay between the genes, and that's why it's really important to understand the molecular basis of what's going on. There are possibly other genes which could need to be dimmed down in this particular area to increase the activity, but it may not be. There's just so many things going on that we need to understand that full picture before we can develop some treatment for it.
Do you think, the promises of genetic manipulation have been great, but have not delivered very much, largely because they are very, very complicated. Do you think you might have simplified it a little?
There are simplifications in terms of this presentation which I've given, but there's also some very simple advances which people have made, which are very, very feasible and tangible. Like there's been a simple chemical discovered which is similar to insulin, and that made the hair cells of mice grow aberrantly. So sometimes it is just a single thing that you're looking at, whereas the problem with this, the mice and the insulin-like chemical they discovered was that the hair cells grew too much. So
what did that do?
That can also damage hearing as well. So too many hair cells or too few is just as damaging. So there are obviously going to be issues like any developmental process, but the underlying genes, yes, they're very complicated, but sometimes it can just be a very simple interaction of one chemical that can produce a massive change.
Thanks.
Thank you.